So in the first video, guys, I walked through how stars are born through nebula and protostar main sequence and then into the red giant phase. This video, we're going to walk through how stars die. And what we're going to do is we're going to focus on our sun first and other stars that are kind of the same mass as our sun. So remember, we finished the first video with red giant either going one way or the other. And it all depends on the mass of the star. So if you have a star that is slightly smaller, 0.8 solar masses, all the way up to 8 times the mass of our sun, you're going to go this way. And what's going to happen is that red giant is going to fuse all of its helium into carbon. And once that happens, the fusion ends. Now these stars are not big enough, don't have enough energy, not a high enough temperature to take carbon and fuse it together. So once that happens, fusion is over. And unfortunately, so is the star. And here's why. What's going to happen is once fusion ends, there's no more pressure force on the inside of the star balancing out force of gravity. So the force of gravity on the inside of the star, on the core, is going to squish that core down even more. But, kind of as we saw in the red giant, it's not going to be strong enough to hold the outer parts of the star together anymore. And what's going to happen is that the outer parts are going to expand even further out into outer space, and it's not going to look like a star anymore. It's going to look something like this. This right here is called a planetary nebula. And planetary nebula is really cool to take a look at. It has all these awesome, beautiful colors. And at the very center, we have this very bright white spot. Okay, that very bright white spot is the remains of the core of the red giant, whereas all these really cool colors are the remains of the outer layers of the red giant. Now, eventually, this planetary nebula is going to turn into something called a white dwarf. And a white dwarf is very similar to a planetary nebula, except all the really cool colors are gone now because the force of gravity can't hold them by the star anymore. Okay, and what a white dwarf is just this remains of the core of the sun or of the star. It is just this big, huge ball of carbon, and it is very bright actually. And the reason why it's so bright is because it's so hot. And white dwarfs are extremely dense. Looks kind of like this. Eventually, though, if you think about it, if the white dwarf is not fusing anything anymore, it's not making any energy, so the temperature is going to eventually get less and less and less as it's releasing that energy into outer space. So as the white dwarf cools down, it's going to not glow anymore. I mean, this process takes billions of years, but the end of our sun and any other star that's in that range of masses will end up as a black dwarf. And a black dwarf is just this really cold, big, huge metal ball of carbon in outer space, just flying around. Okay, so this is what we're ending up as, our sun, black dwarf, big ball of carbon. However, things get a little bit more interesting when you run into stars that are bigger than our sun. So let's talk about those. So again, we're going back to our red giant phase. Now in this case, we have to talk about stars that are bigger than 8 times the solar mass of our sun. So these things are the biggest of the biggest. Now, what's going to happen is since they're so big and they have so much energy and temperature, they can actually fuse the carbon into heavier and heavier elements, all the way up to iron. But again, once we get to iron, this star, once the core is completely iron, it can't take the iron with another iron and fuse them together. There's not enough energy there to do that. So fusion will stop once we hit this iron. And just like what we saw before, once fusion stops, the star begins its death. And in this case, supergiants, okay, here's the sun right here, this tiny little speck. Supergiants are huge, okay? Lots and lots of mass, okay? Remember, whenever we have mass, we also have gravity. Now this thing is so big that the gravitational force, once the pressure force is gone, very, very quickly these supergiants collapse in on themselves very, very fast, and we get a big boom. Okay, we call that a supernova. And this picture over here on the left-hand side is the remnants of a supernova. And the really awesome thing about supernova is it takes all of the elements in the star and it can fuse them into bigger elements even than iron. And when that happens, we get all the elements on the periodic table. Well, most of them. Okay, so that's how we get all of our really heavy elements that we have here on Earth, through supernova. Now, as you can see, after we have a supernova, we can go one of two ways. Again, it depends on the mass, guys. Mass is extremely important when we're talking about where stars go in their life cycle. So after a supernova, the remaining material is continuing to contract, so it's really, really dense. Now, big stars, what they can do over here on the left-hand side is they can turn into something called a neutron star. Now, neutron stars, very, very dense. It's the core of these supergiants shrunk down into a very, very small area. Okay, for example, here's the Earth, here's a white dwarf. That little tiny speck right there, that's a neutron star. So you're taking the core of a supergiant, shrinking it down to something very, very small, even smaller than the moon in some cases, and that's going to make it uber dense. For example, if you were strong enough and you had a strong enough spoon and you could scoop up a teaspoon of a neutron star, it would be the mass of our moon. Okay, these things are very, very dense. So they have very strong gravitational force. However, they're not the objects in the universe that have the most gravitational force. For that, you need the biggest of the biggest stars. When those go supernova, we end up with our black holes. Now, black holes are the objects that have the biggest gravitational attraction. And their gravitational attraction is so big that they don't let matter escape them, and they don't even let light escape them. And light is so fast. I mean, it travels at 300,000 kilometers per second. So for something to have enough gravitational force to keep light in there from it escaping is gigantic. Okay, so that's it. Those are all the different ways stars can end their life cycle. Watch both videos as many times as you need. Nice work, guys.